In this lesson, I'll be taking you through this topic, magnetic induction. I will be going through some basic understanding of this particular topic. So let's say you have a coil of wire like this, and you have a bar magnet close to it. This is a coil of wire. Let's assume that this coil of wire is connected to a kind of meter. If you move this bar magnet close to this coil of wire, an induced current is generated in that coil of wire. So the interaction of this magnetic field and the current that is generated is where this name is taken from. From electric, and magnetic from this magnetic field. So when this magnetic field generated by this bar magnet comes close to this coil of wire, then an induced current is generated. If I move this bar magnet close to this coil of wire, an induced current is generated opposite the direction of the movement of the bar magnet. So in this case, the induced current is flowing in anti-clockwise direction. If I have a coil of wire like this and a bar magnet close to it like this, if I move the bar magnet away from this coil of wire, then the induced current is going to flow in the opposite direction. So essentially, the interaction between a bar magnet with its magnetic field and a coil of wire is what brings this electromagnetic induction. So now we use two symbols to show the direction of the magnetic field. We use X to say that a magnetic field is entering into the page. So we say X is into the page and dot is out of the page. Dot is out of the page. Yes, as we go along in this, I'm going to show you where we will use this and where we use this. So essentially, if you bring a bar magnet close to this coil, we can say that it is into the page and also out of the page. So I can represent the two. So this one, I can put dot here. This one is going into the page. This one is going out of the page. Of course, the two can happen simultaneously, and I will show you where that applies. So that is that essentially. When you bring bar magnet close to a wire, something is going to happen. An induced current is going to be generated around that coil of wire. When you move it out, an induced current is also generated. Now the direction of this one is opposite the direction of this, while the direction of this also is opposite to the direction of this. So that is just the basic understanding of this electromagnetic induction. I'm going to show you more, and as we go along, I'm going to also explain in detail what this is all about. So now let's talk about some basic formulas that we will use in electromagnetic induction. The first formula I would like to introduce you to is this. This formula is very important. So what does this stand for? This is magnetic flux. So if you want to calculate the magnetic flux, you are going to multiply the magnetic field strength by the area of the coil of wire that you are using, and you multiply by the cosine of the angle between the coil of wire and the magnetic field. I'm going to show you all that. So this is magnetic flux, and this B stands for magnetic field. A is the area of the coil of wire. Then theta is the angle of inclination. So this is very important. I want you to keep it somewhere. Then the second formula that I would give you is the induced EMF. Notice that where I drew this diagram for you the other time, I wrote I here. This is induced current. It can also be induced EMF because when you know your EMF, you can also calculate your current. So induced EMF is minus change in magnetic flux minus n, then change in magnetic flux over change in time. So where this n is equal to number of coil of wire or number of turns, number of turns of the coil of the coil. Then this symbol means change in magnetic flux. So this change in magnetic flux, I'm going to explain. This change in magnetic flux is determined by how fast or how slow the you are bringing the movement of the bar magnet inside the coil. If the movement of the bar magnet inside the coil is fast, then this change in magnetic flux will be much. But if it is slow, then the change in magnetic flux will be small. So then this one is change in time. Change in time. And it is important for you to know that since magnetic flux is equal to this, I can write minus n b a cos theta over dt. Please, I want you to note, let me explain the meaning of this n. The meaning of this, sorry, minus. The meaning of this minus is, that minus is only showing the direction of the induced EMF or the induced current. You know, I showed you the other time that when this is your meter, when you bring a bar magnet, this is a bar magnet. When you bring it close to this coil of wire, your induced EMF or your induced current flows in opposite direction. So that opposite direction is what this minus is standing for. So meaning that even if you are calculating, your calculation should not be affected by this minus. Meaning that your answer should not carry minus, or don't worry, just do your solution or do your solvings. But this minus just stands for to show you the direction of the induced EMF or the induced current. So that is that. Then I also want to explain this before I leave this side. Then I want to explain that, I mentioned it here, but I want to explain it again. That this is your meter, this is your bar magnet. If you move this bar magnet, if you move it fast, if the movement is fast towards the coil of wire, the induced EMF or the induced current here will be much compared to when you are moving it slowly. So if I move it fast, it will be much. But if I move it slowly towards this coil of wire, the induced EMF or the induced current will be small. So meaning that the faster the movement of the bar magnet towards the coil of wire, the much the induced current or the induced EMF. So when you move it slowly, the induced EMF or the induced current will be small. So let me also point that out. So when you move it fast, so that is actually what we are trying to explain here is you have seen it around you. You know generator. Inside generator, we have alternator. Alternator is what gives us the light that we use. So we have the mechanical part in the generator, we have the electrical part. The electrical part is made up of coil of wire and a magnet. So when the mechanical part starts working, it makes sure that the coil of the magnet inside that coil of wire is rotating very fast. As it's rotating very fast, it's generating a very big induced EMF through those coil, and that is what gives you the electricity in the house. So when the coil of wire is moving fast, or when the bar magnet is moving fast around the coil of wire, then the electricity that will be generated will be much. So that is that. Then another formula that I need you to point to take note of is, okay, sorry, this is another, okay, E is equal to IR, meaning that this I is current flowing, or current induced current. Let me just call it induced current. Then R is resistance of the coil. Resistance of the coil. So if a particular question asks you to find the current induced or the induced current, so just come here, find your induced EMF first of all. Once you find your induced EMF, then you can use this formula to find your induced current. Of course, in the question, you must have been given your resistance. So once you have your resistance, you can calculate your induced EMF, and using induced EMF and your resistance, you can calculate your induced current. So these are the basic formula. This is the first one, which we are going to use in our calculation. This is the third one. This is the fourth one. Also, this, let me also add this. You might be asked to calculate the power generated in the coil. Power can be IV or I square R. I is the induced current. You already know induced current. Then V is the voltage. Now, your voltage here is also equal to your EMF, please. Don't forget. Then then R is resistance. So you can be asked to calculate power, you can be asked to calculate. So if you have current and voltage, you can calculate power, or if you have current and resistance, you can calculate your power. So that is that. Now let's talk about the factors affecting induced EMF. We have discussed the basic understanding of electromagnetic induction. We have spoken about or discussed the basic formulas. Now we are on the factors affecting the induced EMF in a coil. Now the first factor here is rate of change of magnetic flux. And then the second one is the number of turns in a coil. Third one is the magnetic field strength. And the fourth one is the angle of inclination. So I will be explaining where I took this from and what it means. Now remember what we wrote is factors affecting the induced EMF. What was the formula of induced EMF the other time? We said induced EMF is N di over dt, which is also equal to N BA cos theta over dt. Now, this rate of change of magnetic flux, this is it. Remember the other time I said the I is rate of change. So this rate of change of magnetic flux affects induced EMF. That's the first one. The number of turns, N, this N you are seeing stands for number of turns. The number of turns affects the induced EMF. Another one is magnetic field strength. This B you are seeing is magnetic field strength. And then angle of inclination, this theta that you are seeing is angle of inclination. So what does it mean when they say rate of change of magnetic flux? Remember, I said the other time that the induced EMF is dependent on how fast the magnet is moving close or moving out of a coil. So when the motion is very fast, is moving close and moving out, or is rotating very fast, then that gives induced EMF an ability or a chance to be induced more. So you have more induced EMF if the rate of change is very fast. The rate of change just means how fast the magnet is rotating or is moving close or out of a coil. Then number of turns means that if you have a circle, maybe a circular coil like this, it will be different. The induced EMF in a single circular coil will be different from if you have a several circular coils, or like this. Let me show you like this. If you have it like this, let's assume that a coil of wire is like this, and you have to pass a magnet. Yeah, this is NS. If you are to pass a magnet into this coil of wire, let's assume this is a several coil of wire and magnets can enter into it. So every part of this coil of wire will touch all the magnetic field around this magnet. So because this has a chance of touching all the magnetic field around this magnet, there will be more induced EMF around this compared to this and compared to this. This will have very low induced EMF. This will have a little more induced EMF, but this will have much induced EMF because of the number of turns. We have several number of turns here compared to this and compared to this. So number of turns, if you have high number of turns, you have very high induced current. Then the third one is magnetic field strength. If you are using a magnet that has a very low magnetic field strength, your induced EMF will be very small. But if you are using a magnet with a very high magnetic field strength, you are going to have a very high induced EMF. And then the last one is the angle of inclination. I want to show you using diagrams this angle of inclination. Now let's assume that we have a plane. Let's just assume we have a plane of coil like this. Let's assume we have a plane of coil like this. Now, here is considered as the normal. N here is considered as the normal. And then we have another one that has normal just like that. This is N again. Then we have another one that has normal like that. So this is, let's assume our coil is around here. Our coil of wire is around here. Our coil of wire is around here. So now if our magnet is coming in this direction, okay, if our bar magnet is inclined parallel to the coil of wire, this is how the coil of wire is, like this. So if a bar magnet, this is B, is inclined parallel to that coil of wire, we have the angle between that will be 90 degrees. Then if our magnet is inclined at a particular angle, this is our magnet, we have, for this one, our theta is equal to 90 degrees. Our theta is equal to 90 degrees. And then here, if our magnetic field is inclined perpendicular, this is perpendicular to the coil of wire, our theta here will be 0. Our theta here will be 0 degrees. So now this is our theta here. We have theta here. So this will affect, if we have, this is our magnetic flux. Remember, magnetic flux is BA cos theta, and BA cos 90 will give us 0. So there will not be any magnetic flux here. This one will be 0. And then since our magnetic field is inclined at an angle here, your magnetic flux for this one will be BA, simply BA cos theta. But for here, your magnetic flux is, remember, is BA cos theta, and your magnetic flux will be BA cos 0. Cos 0 will give you 1. So 1 multiplied by BA will be BA. Your induced EMF is greatest when you have your magnetic field perpendicular. So this one is perpendicular. When you hear perpendicular to the magnetic field, perpendicular to the magnetic field, perpendicular to the, no, not magnetic field, perpendicular to the coil of wire. When your magnetic field is perpendicular to the coil of wire, your theta is equal to 0. When it is perpendicular to the coil of wire, like this is coil of wire, this is your magnetic field entering it. When it is perpendicular in this way, your theta is equal to 0. If your theta is 0, then you have the greatest magnetic flux when your magnetic field is perpendicular to the coil of wire. So just assume that this coil of wire is like this, in this case, and then your magnetic field is like this. So if it is like that, then your theta is equal to 0, and your magnetic flux is greatest when your magnetic field is perpendicular to the coil of wire. Then this is magnetic field inclined at an angle. It can be, this angle can be 30, it can be 20, it can be 60, it can be any acute angle. Then here, this is parallel. We say this one is parallel. Now, when your magnetic field is parallel to the coil of wire, you have 90 degrees. When it is 90 degrees, you have 0 induced EMF. So this angle of inclination affect the induced EMF in that when it is perpendicular, then you have the greatest. When it is parallel, you have the lowest or almost 0. Then if you have any angle in between 0 and 90 degrees, you can always calculate the magnetic flux that is. So let's talk about the basic right-hand rule. So imagine you have a coil of a single current carrying wire, or a coil like this, and a current is flowing in this direction. This is the direction of the current. Now, if current is flowing in this direction, then a wire or a coil that is carrying current will generate a magnetic field. So when a wire is carrying current, magnetic field will be generated around the wire or around the coil. Now, the direction of this magnetic field generated around a current carrying coil will be determined by right-hand rule. So how do we do that? I want you to hold your pen up like this. If you grip your pen like this, while sticking it upwards, then your thumb will represent the direction of the flow of the current. Look at this. While the remaining 4 fingers will represent the direction of the magnetic field around that coil. What do I mean? So grip your pen like this. Let your thumb face up, just like this. So this is the direction of the current, just like I've drawn on the board, and this is the magnetic field around this coil. This pen is the coil of wire that is carrying current. This thumb is the direction of the current, while these 4 fingers is the direction of the magnetic field generated around this coil of wire. So the other time I showed you a symbol, I said X represents into the page, Y dot represents out of the page. So we say that since my finger is curled around this pen this way, we say that this end is into the page, is going into the page, while this other end is out of the page. So now we write X here as into the page and dot here as out of the page. And the same thing happens if current is flowing in this direction. This is current. So this will be flipped. Why this one is into the page and this was out of the page. In this case, since current is flowing in the opposite direction now, this will be into the page, while this will be out of the page. So that is the basic principle of right hand rule. And let me just show you using a simple diagram. This is pardon me for my drawing skills. So this is your pen, and okay, good. So this term represents the flow of current, the direction of the flow of current, while this represents the direction of the flow of magnetic field around it. So this is into the page, while this is out of the page. So that is just the simple explanation of the direction of magnetic field depending on the direction of the flow of current. So you might be asked anytime. This is just, so once you are asked, just remember this right hand rule. You'll be able to figure out what the right answer should be. Thank you. Some examples that I want us to consider together. We have discussed basic understanding, basic formula, the factors, the right hand rule, and yeah, examples. So I want us to solve this together. Number one says a coil has a resistance of 4 ohms and an induced EMF of 12 volts. A says calculate the induced current in the coil. B says if resistance is doubled, calculate the current. That's the first question. And the second one is a coil of 250 tons and a cross-sectional area of 0.04 meters squared is placed in a uniform magnetic field of 0.6 Tesla. The plane of the coil is perpendicular to the magnetic field. Full stop. Calculate A, the magnetic flux through 1 ton of the coil. And the second one says calculate the total magnetic flux linkage. So we want to consider these together. You can write it down so that because I know you are learning, so you can write it down and then we'll solve it together. Now, the first one is, now anytime you want to solve physics question, the first thing you need to do is that list out all your parameters. For example, in this number one, you are given resistance of 4 ohms and induced EMF of 12 volts. So list that out. Once you list that out, you are good to go. Then the second one, you list everything you are given, so that listing it alone gives you a direction. You already know what you have and what you don't have. That's the first thing. Then the second thing is that understand what they ask you to find. Don't start looking for what they don't ask you to find. Don't start solving what you are not asked to solve. So first of all, list the parameters that you are given and understand what you are asked to solve. And then once you do that too, you are good to go. Now the first one says we are giving resistance in the first one. So you write R is equal to 4 ohms. That's your resistance. And induced EMF, E is equal to 12 volts. A says calculates the induced current. So we don't have induced current, but we know that E is equal to IR, and I can make I the subject of formula as E over R. So I is equal to E is 12 over R is 4. So my current is equal to 3 ampere. So I'm done with the first one. This is A. Then B. They say if the resistance is doubled, calculate the current. Now, they said we should double the resistance, but the induced EMF remains the same. Then we are now doubling the resistance. The resistance formerly was 4. If we double it, it will give us 8 ohms. Now, let's calculate the current. Current is equal to E over R. Current is equal to 12 over 8. And that gives us 1.5 ampere. So you can take a screenshot and write down the solution. So let's go to the second one. The second one, number 2. the second one, in this second one, we are given number of turns. Remember, n is equal to number of turns, which is 250 in this question. And then your cross-sectional area, the capital letter A is equal to 0.04 meters squared. And is placed in a uniform magnetic field of 0.6 Tesla. So B is equal to 0.6 Tesla. The plane is perpendicular to the coil of the plane of the coil is perpendicular to the magnetic field. Anytime you hear perpendicular, the angle is 0. I've told you the other time. So now area is measured in meters squared. The magnetic field is measured in Tesla, that is T. Then your magnetic flux is measured in Weber. Usually we write it as WB, just ordinary WB, but the full name is Weber. The full name of this capital letter T is Tesla, and area, like you know, is measured in meters squared. So if you are given another question, if you are given centimeter square or millimeter square, you need to convert it to meter square before you use it to solve your question. A says that we should calculate the magnetic flux through 1 turn of the coil. Magnetic flux through 1 turn. So our magnetic flux is equal to BA cos theta. Our magnetic flux is BA cos 0. We already know 0 degree. We already know that 0 cos 0 degree, cosine 0 degree is going to give us 1. If you multiply that one with BA, you have ordinary BA. So just multiply B, which is 0.6 Tesla, times area 0.04 meter squared, and your answer is going to give you 0.024 Weber, like I gave you here, Weber. So that's the answer here. B says calculate the total magnetic flux linkage. So total magnetic linkage or flux linkage. Total magnetic flux is equal to N multiplied by your, since this is the magnetic flux through 1 turn. Look at this, 1 turn of the coil, and we have 250 turn. So if the magnetic flux through 1 turn is 0.024, then if you want to calculate through 250 turns, just multiply this by 250. So 250 multiplied by 0.024 Weber is going to give us 6.0 Weber. So you can take a screenshot or pause this video and check the question, check the solution, and make sure you master it. And please don't forget to like and subscribe to this channel, so that anytime I upload lesson like this, you can always have get notified. Let us consider 3 more questions, number 3, 4, and 5. Number 3 says a coil of 150 tons experiences a change in magnetic flux from 0.02 Weber to 0.005 Weber in 0.10 seconds. Calculate the induced EMF in the coil. Then this is the 4th, this is the 5th. So let us consider, or let us solve this number 3. Remember, I told you that if you are given a physics question, first list out your parameters. Now, the first parameter given here is N, which is our number of turn, 150, experiences a change in magnetic flux from 0.02. So the first magnetic flux is 0.020 Weber, and the second one is 0.005 Weber. In change in time, 0.10 seconds. Calculate the induced EMF. Remember, the formula of our induced EMF is E is equal to N, the change in magnetic flux over change in time. E is equal to, our N is 150, open bracket, you are going to subtract 0.02 minus 0.005 all over 0.1, this is seconds. Then E is equal to 150. If you multiply this from this, it will give you 0.015 all over 0.1. And your answer will be 22.5 volts. So that is your answer for this particular question, 22.5 volts. So you can pause this video and read the question again, check the parameters and check how we solved it. So that is number 3. I want to clean it now. Then let's go to number 4. Number 4. Number 4 says a rectangular coil of area 0.12 meters. The first parameter here is 0.12 meter square. That is our area. It is inclined at an angle 60 degrees to the magnetic field strength of 0.8 Tesla. Calculate the magnetic flux through the coil. We want to calculate the magnetic flux. Remember, the formula for our magnetic flux is this is equal to BA cos theta. So just write your B is 0.8 multiplied by A 0.12, then multiplied by cos 60. 0.8 times 0.12 times cos 60 will give us 0.5. Then the answer to this is going to be 0.048 Weber. That's the answer to that. So you can also pause this video, check this question, compare it with these parameters that I've listed out, and check how I solved it. So let me clean that and let's go to number 5. This piece. N is equal to 400. Then it is placed, okay, area is equal to 0.025 meters squared. It is placed in a magnetic field of B, that's magnetic field of 0.5 Tesla, and in 0.2 seconds, the T is equal to 0.2 seconds. Okay, so I've managed the space. Calculate, first thing we need to calculate is the initial magnetic flux. So the initial magnetic flux will be BA cos I didn't list the angle. The first angle is 0 degrees, while the second angle is 90 degrees. So A says we should calculate the initial magnetic flux. That will be BA cos theta 1. So B is 0.5 multiplied by 0.025, then multiplied by cos 0 degrees. 0.5 times 0.025, cos 0 degree will give us 1. So 0.0125 Weber. Then B, we are still going to use the same formula because B says we should calculate the final flux, final magnetic flux. We are using the same formula, but with the second angle. This is going to be BA cos 90 degrees. And since we know that cos 90 is going to give us 0, so this will be equal to 0 Weber. Then C, induced EMF. Induced EMF, we are going to use NBA cos theta. Okay. No, let us use this. And the change in magnetic flux over dt. So E is equal to N. N is 400 times, we are going to subtract this from this. So this is going to be open bracket 0.0125 minus 0. The initial magnetic flux minus the final magnetic flux. So this is the initial magnetic flux, this is the final magnetic flux over the T, which is 0.2, is it 25 or 2 seconds? Okay, just 0.2 seconds. This is going to be 400 multiplied by 0.0125 all over 0.2. And this is going to give us 25. If you do the calculation, it's going to give you 25 volts. So that is that. So we have solved 5 questions in total, and this is how they usually come out. To give you your own 5 questions, that's the task here. I'm going to write 5 questions. You are going to pause the video, copy out the questions, and then you are going to try them by yourself. Here are questions for you to solve. So you can pause this video here and screenshot them. Screenshot the page, then copy it out and solve them for yourself. The formulas that you're going to use, I've shared them. How you're going to solve them, I've also shared with you. List out the parameters, then use the appropriate formulas. You are going to get your answer. So good luck. Don't forget to like this video, to subscribe to this channel, and to also share it to students like you that you know will benefit from this video. Thank you.